All right, so now probably the most useful thing I can teach you in MATLAB for saving you work in your future courses. When I teach mechanics, I always try to get people to use MATLAB to save themselves a lot of algebraic work, and people are just really resistant to do it. But here's a typical mechanics problem. And this particular problem, by the way, it's you take a rod, hard to do this on camera, but you take a rod, you set it at an angle, and you release it, and then it falls and rotates at the same time. So the question is, at the instant you release it, what's the acceleration of the center of mass? And what's the angular acceleration? So how quickly is the center of mass falling? And how quickly is it rotating in terms of acceleration? So I'm not going to derive the equations for you. I do it in my mechanics class, or actually I make them do it. But here are the equations. The first two are just F equals ma. You sum the forces in the vertical and horizontal directions. Set it equal to m times the component of the acceleration. The third one is a constraint equation. Basically, where it comes from is the fact that one end of the rod is on the table. So you know that that end of the rod can only move horizontally. Okay, that constraint leads to this equation. And the fourth one is I'm sorry, that's the fourth one. The fourth one is the constraint equation. The third one is the rotational equivalent of Newton's second law, where the sum of the moments equals the moment of inertia times the angular acceleration. Okay, so this is F equals ma. This is tau equals I alpha. All right, so those are the four equations. How do you set them up in MATLAB so you can solve them? Well, you set them up as a matrix. And what gets confusing for people is you got all these symbols, and you have to think about which of these symbols are variables that I'm trying to solve for, and which ones are parameters for which I already have numbers. And so what we're trying to solve for is the accelerations, ax, ay, alpha is the angular acceleration, and the other unknown is the normal force. Okay, that's the normal force between the end of the rod and the table. So those are the four variables: ax, ay, alpha, and n. You then pick out the coefficients of each of those variables and put them in a matrix. And remember, when you do this, you have to make sure you write all the equations with the variables in the same order, which I didn't necessarily do here. Okay. But it's going to be, if you look at the coefficient, first equation, the coefficient of the ax term is m. It doesn't have ay or alpha in it, so you put zeros for those. And it's one thing that trips people up. They forget to put in the zeros. And then the coefficient of the capital N term, that's another variable, is minus mu k, so that goes there. Then the second equation, there's no ax term, so that's a 0. Coefficient of ay is m. There's no alpha term. And the coefficient of the n term is minus 1. That's the other thing people get confused about. They don't know what to do when there's no number here. Well, there's no number, it's just a 1. Or in this case, it's a minus 1. Third equation doesn't have ax or ay, so we have 2 zeros. Coefficient for alpha is 1/12 ml squared. And the coefficient for n is minus L over 2 mu k sine theta minus cos theta. And I just changed the sign here, just factored through that minus sign. And then the fourth equation, 0, 1 for the ay term, minus L over 2 cos theta for the alpha term, and there's no n term. All right, so that's the matrix. But the other thing you need is the constant terms. Okay, anything that doesn't have any of the variables in it goes to the right-hand side. And only one equation has a constant term because there's only one force in the problem. Well, one known force in the problem, one forcing, how should I put it? Forcing influence, applied force. So that's the weight. You take that to the right-hand side, it's going to become negative. So it's minus mg. All right, so setting it up is just knowing basic algebra. Now, how do you solve it in MATLAB? Well, you create this matrix and you create this vector. All right, so you put in the parameters, you create the matrix, you create the vector. And we're not doing it symbolically here. We don't do any symbolic math in this class. We're just doing it numerically. Okay, so we're solving it for a given set of values of this parameter, these parameters. MATLAB can do it symbolically as well, but that's beyond the scope of what we want to do here. All right, so given M and V, how do you then solve for AX, AY, alpha, and N? It's just one command, M\V. So this is the left division operator that I mentioned briefly on the first day of class. And I said the only time you actually use that is when you're solving a system of linear equations. So that's what we're doing here. And people just really have a hard time wrapping their brain around this. What is it doing? It doesn't matter what it's doing. Just learn this syntax. If you have a matrix equation like this with a matrix M and a vector V, to solve that system of equations, you do M\V. And it's doing some fairly complex algorithm. You know, there are different algorithms for solving systems of linear equations. You might have learned Gaussian elimination at one point, but it's doing something like that. And in fact, it's pretty good at even adapting the algorithm depending on the characteristics of the matrix. Okay. All right, so it gave you back a vector y. Well, what is that? Well, that's the values of these four variables, AX, AY, alpha, and N. Okay, so first one is AX, second one is AY, third one is alpha, fourth one is N. Just because that's the order I wrote the variables in when I set up the equations. All right. And I took the two components of the linear acceleration, and I wrote it in IJ notation, right, as a vector. And by the way, here's a little trick. If you want to print out a superscript, and you can do all kinds of things like this, special characters with fprintf, look up the Unicode for it. Okay, I just looked up the Unicode for a superscript 2. Turns out it's 00B2. So to print that with fprintf, you do \x and then that Unicode. Okay. All right, then the third one's the angular acceleration in radians per second squared. And the fourth one is the normal force. All right, so you should know how to do all this. You should know how to set up a matrix and a vector, of course. So the new trick here is just knowing this little thing. This is how you tell MATLAB to solve a system of linear equations. All right, and then the problem in the exercise is a circuit, but don't worry if you don't know circuits because we're giving you the equations. All right, so if you apply Kirchhoff's rules to this circuit, you'll get these four equations. You just have to understand what's a constant here, what's a parameter, and what are you solving for? What you're solving for is the currents, I1, I2, I3, and I4. Okay, so it's already written in the form that should make it easy to set up the matrix. Okay, R1, R2, 0, 0. R1, 0, because there's no I2 term here. R3 minus R4. 0, R2 minus R3, 0. 1 minus 1 minus 1, 0. Right? That's the matrix. And then the vector, the right-hand sides, 15, 0, 0, 0. Now, one more little detail. Back at the beginning of the course, I said, for what we're doing, it doesn't really matter if you use row vectors or column vectors. This is the one time it matters. Okay, notice I made this vector a column vector. It has to be a column vector for this to work. All right. So this 15, 0, 0, 0, that has to be a column vector. All right, so you look at these equations, you set up the matrix, you set up the vector for the right-hand side, you solve for the currents, And then you can compare it against this output. I did this using a little circuit simulator, and you should get the same set of numbers.